Okay, let's go ahead and get started. So thank you for the introduction, Jitendra. I'm very happy to be here. This is a bit of a homecoming for me because from October 2010 until June of 2011, I was based here. I was doing a postdoc and I was working with Professor Sudipta Mukherjee, and I was working on this wheelchair that you see in this picture. And so during that year, I lived in India. We made prototypes of this chair. We tested them all over the country. And that was a really transformative experience for me. And also, I think, really got me tied into India. And I've been coming back. I've probably been to India 30 or more times over that period. And actually, most of my research group now does work in India with partners like Mahindra and Tata, Jain Irrigation, Eureka Forbes. So we have a very tight contact with India. And the main, the main theme of this course over the next 2 days is I'm trying to share with you what my research group does as far as how we approach designing for developing and emerging markets like India, and bringing together this marriage of trying to understand the unique user-centered and socioeconomic factors of those markets, and tying into that rigorous machine design research, the physics-based, math-based research that describe how a technology is going to behave. So we're going to look at that theme from a variety of angles. The theme overall I'm going to call global engineering. That's what I call what my group does. My group's name is the Global Engineering and Research Lab. And I'll give you a bunch of examples of the different types of work that we do. Also, during this course, I want you to ask questions and talk. I'm going to be asking you, for feedback throughout the course as well. So let's go ahead and get started. And I think the first is why. So I grew up in America. I focus on design. I would say historically, design thinking, product design has been focused really towards Western, American, European markets. But I think there's great opportunities, as I'm sure all of you experience, you living in India, for designing products specifically for developing and emerging markets and really burgeoning markets like India. It's been amazing working in India for almost the last 10 years, seeing just the growth of this country in the time I've been here. Culturally, it's changed a lot. It's continuing to grow economically. And so I think it's a space that is worth thinking about how do we design successfully for that context. So there's a few reasons why I think that's important. The first is when you look at lower resource settings throughout the world, there's many global challenges that persist for decades and decades and decades that remain unsolved. And so an example of this is if you look at the Sustainable Development Goals, and these are all metrics for human health and well-being. These were set out in 2015. That they want to completely eradicate all of the issues associated with all of these 17 areas of issue around the world. To give you a little background, these were extensions from the Millennium Development Goals. And so in the year 2000, the UN set out goals for progressing or reduction in poverty and health and water and sanitation for people around the world. And they wanted to do it in 15 years, by 2015. What happened is about half the goals met their requirement, which was reducing the population that are affected by those issues in half. But even though some of those goals were successful, you still have about 1 billion people throughout the world in absolute poverty. You still have about 2 billion who don't have access to clean water and sanitation. And so what's interesting to me is that you look at these measures of human well-being, and hundreds of millions and billions of people still are affected by these issues. And what's particularly interesting is that if you're from a wealthy family, or if you grew up in the US and Europe, a lot of these issues have been greatly reduced. Like living in Boston, I don't worry about clean water or my sanitation system, right? We have solutions for that work. But for some reason, those solutions don't map over to low resource settings. right? So even though we have technologies to improve health and water quality and energy and all these factors, they don't necessarily work in lower resource setting countries. And so I think that's an opportunity for us as engineers to think about why is that, and could we apply engineering to maybe alleviate those problems? The next point is that I think if I, particularly as a Westerner, think about the demographics of people that have been designed for with product design over decades, the needs of those people may be very different than the needs of people in developing and emerging markets. And so, I think if you're here at a school like IIT Delhi, I don't think any of us went out to gather our fuel source for cooking or bathing this morning, right? Like you are all at a socioeconomic level because you've reached this school, or will be, after you graduate, that you probably won't do this in your life, and I won't either. I do some work on tractors, and what's interesting about tractors in India is that typically half the time a tractor is used in India is for operations other than farming. It's like haulage operations. And so if you design a tractor in this country only for farming, you may be missing some of the needs of the farmer, how they have to use this tractor to make money. And then this picture of 4 people on a motorcycle here in India, I think you've all seen this, right? I've seen this many times in this country. In the United States, these people would be arrested, right? And their children would be taken away from them by the government because this is highly illegal, right? But here it's like, people do it. And like that's a family vehicle, right? That's how people get around. And so like if I'm thinking about designing a vehicle for family here, I can't think from my, only Western perspective. I have to think about our cultural differences important to consider. I have to understand that. We all have to understand this. And then the final point is that I think with the rapid growth, particularly of countries like India, there's really powerful opportunities to make multi-market technologies that can work in maybe a lower cost context, but provide tremendous value so they can go back to a wealthy country and be disruptive. They can be a high performance, low cost solution. And the canonical example in this space was this ultrasound machine that was designed by General Electric. And so it was done in the mid to early 2000s. So the backstory of this is that General Electric made ultrasound machines like the one on the left here, which cost $100,000 for a hospital to buy. And at that time, they were making a big push to get into China and sell these machines in China. And they very quickly realized that hospitals, only the richest hospitals would buy the high-cost machines, but most hospitals just wouldn't buy this. And the critical insight that GE was able to make was that the Chinese market was willing to accept lower performance than this high-cost US-based machine. They would accept 50% the performance of that machine, but it had to cost 15% as much. So this is like an example of what I'm talking about, a relatively high performance to its cost. They're scaling down cost much more than they're scaling down performance. And because they realized those different requirements for design, they were able to design this new device. It kind of looks like a laptop. They've actually shrunk it even more. It looks like a cell phone now. But they were able to design this high-performance, low-cost solution. This product helped GE become the biggest seller of medical devices in China. It sold incredibly well throughout the country. But it also opened up new markets around the world that previously could not afford an ultrasound machine, like ambulance drivers in the US or rural areas, smaller clinics in the US, which before would not be able to afford it, but now could afford an ultrasound. So they were able to leverage the constraints of an emerging market to push high performance, low cost, create this very high value technology that was successfully sold globally. I think another cool example of this is how shampoo has been sold in markets like including India, where if you contrast how it's sold in the US, it's common for consumers like me to go to a big grocery store and buy big, these bottles are like this big, they're huge, they're almost a liter of shampoo, and they're relatively expensive, but per volume they're reasonably low cost, but we have the room to put them in our shower, and that's how people like buying things. And the shampoo companies realized that people in markets like India don't want to buy a big volume of shampoo like that. And they realized that they could sell the same shampoo product, same chemical, but in small sachets. So people could buy single-use servings of shampoo. And so now, just because of that packaging insight, there's as much shampoo sold by volume in like India versus the US probably per capita, but it's only feasible because they changed the packaging, right? I think that's really, really cool. So I think it's also important for us when we're thinking about multi-market opportunities to certainly consider what we would call maybe poor consumers. I think I deal with a lot of people in academia who work in design for developing countries who think of the poorest of the poor, meeting their needs. These are typically people who have not been designed for in the past. But I think it's also important for us to remember, like in a country like India, economically over the last generation, this country's changed drastically. You have more middle-class people in this country than we have citizens in the US, right? Like more than 300 million people who are like middle-class consumers. And so I think it's really important for us to think holistically about the economic pyramid in developing and emerging markets, that we're not just designing for like $2 a day people. We can design for $10, $100, $1,000 per day people. Like all of those, you have probably some of the most, or like maybe one of the greatest quantities of billionaires probably of a country in the world. Like there's very rich people in this country as well as very poor people. And so I think it's important to think of that entire ecosystem. And measures of that is what are called the BRIC economies, China, India, Russia, Brazil, are growing very, very quickly. They're going to continue to be greater and greater players economically in the world. And even if a country like the US is still a big economy, the rate of change of an economy like China or India is much faster than the US. And so if you are a shrewd multinational company, you need to be looking at emerging markets to say, that's where all the growth is. We need to figure out how to tap into those markets. And so we as designers, I think, have to think about that too. So one thing I want to be thinking about in this course is how do we engineer products for global impact? Can we design them globally, and can we design products that will ideally span a large economic pyramid? So this all ties into what my research group does at MIT, the Global Engineering Research Lab. So what we try to do is kind of two parts. We first try to understand the landscape behind a problem in a developing and emerging market, and understand it from both a technical standpoint, like what are the governing physics behind the problem, and a socioeconomic standpoint, in understanding like what are cultural practices, how much resources can people allocate to a solution. Then what we do is use that perspective to enable us to design new technologies and design really tricky, difficult to design technologies by leveraging research, product design and machine design research, in order to create high performance, low cost, and globally relevant technologies. And so the main areas that we work in, and you'll hear more about some of these over the next 2 days, are water, power, agriculture, and mobility. Actually, these are all 4 Indian pictures, which is cool because we do a lot of work in India. And a prevailing theme in a lot of our work is that we often are faced with trying to solve a challenge in a new market where there's been an existing technology, let's say in the United States, that has been successful. Let's say it's around clean water, right? People afford it, people get the clean water, but for some reason that technology, like I was saying before, hasn't mapped over to a poorer country. And the reason is that we find often is because of a price-performance mismatch. And so what I mean by that is that people in a low-resource setting may want a relatively high-performance technology. Like nobody wants a semi-functional sanitation system, right? It's not like you can say to somebody like, okay, we're going to give you sanitation that works 70% of the time. And it's like, ugh, I don't want to get sick that other 30%. So like there's a number of products, or like maternal health. Like no mother wants their children to die some percentage of the time. Like you want that thing to work, right? So there's technologies where you want it to work, you want a certain level of performance, but in the US market, that may cost a relatively high amount of money, say up here. And the problem is that when you go to a poorer country, the price point they may be able to afford is here. And why that creates an issue is that if you take any family of technology, right, let's say automobiles, they're going to lie on a price performance curve that's nonlinear. So you may have your like Toyota Corolla solution, Tata Nano solution down here, and like your Ferrari type solution up here. And if we look at a technology that's offered in the US and we try to make it cheaper for an emerging market, we may end up compromising the performance. And so what's important for my group to realize all the time is what are the specific requirements being dictated by the country we're trying to design for, and are they different than a point that lies on this existing technology curve? And so if we can see that difference, we can realize there's no real way to adapt our way down the existing technology curve. We have to somehow disrupt. We have to somehow jump off that curve and hit this new price performance point. And so we do this by combining together these physics views of problems and socioeconomic insights to create these disruptive solutions, high performance, low cost solutions. And then what we also try to do is say, okay, if we make this high performance, low cost solution for a low resource setting, could that be disruptive back in a wealthier market? And the term for this is reverse innovation, where you can maybe change features a little bit, maybe add some features, and make a whole new product family out of your new high value solution and sell it to poor markets and rich markets at the same time through reverse innovation. And I did a paper on this a few years ago, which you can Google and read about this. There's actually 2 papers that talk about this in HBR. So we try to keep this global context and try to create high value in a global context. And so, the areas that we work in is we've done a lot of work in wheelchairs. You'll see some about this today. We do a lot of work in desalination and irrigation, all water-related topics. We work on prosthetic limbs, and we also do powertrain work in tractors and engine stuff. So we have a portfolio of work that we do in my group. One thing that I want you to reflect on in this course is what type of engineer you want to be. There's a popular cartoon in the US called Dilbert. Do you have this cartoon here? Well, this is a character, a cartoon character who, he works in an office and he's always working in his cubicle, and he's saying here, I'm the king of my cubicle, the absolute ruler of this tiny realm. Think about the perspective as a designer this guy would have if their only perspective is their cubicle. It's like walking through the world with your hands over your eyes. You can't see what's going on around you. Another example of this, picture this. Anybody recognize this movie? I don't know if this was popular here. It was a movie called Office Space, but it was a guy like relegated to his cubicle. He like never left it. And my point here is that you don't want to be a designer where your only perspective is your own mind. I can see actually one critical perspective that's missing from society in this room. Do you know what perspective that is? That none of us has? We're all men in this room, right? Like if you have to design products for women, you better recognize really quickly you're not a woman, right? And that you may not understand their needs, their desires, what they want in a product, right? So history is like filled with these like terrible like products that, like in the 1950s in the US, men would design like sanitary pads or like brassieres or like all these things for women, and women would be like, oh, these are terrible, because they're not women. So anyway, you want to be able to see outside your own context is one important point. The next thing, if we're talking about designing for low resource settings, I would encourage you to think about like your motivations and how you interact with those settings. So, this is a picture of Angelina Jolie, who is a movie star. She does really good work for the UN. United Nations, but the dynamic in this picture I think is really interesting in that she's clearly going to another country and she's kind of bestowing something on the population there. And so everybody in this room is from a very privileged demographic in this country, right? You are the top of the top of the top if you're at a place like IIT Delhi. And so I think it's important to recognize that dynamic. Let's say if you're going into a poor village, that you don't want to come in as like the great savior to save all these people. Like, I know more because I'm smart and wealthy and from a great academic background. You know nothing. I'm going to give you something. You want to be very careful of that dynamic and not being like high and mighty necessarily. So think about how you're going to behave as an engineer. I think this issue happens I do some work with IIT Bombay, but I'm sure it happens here too. Definitely happens throughout US universities, of this idea of like, you can send students to a poor community and they can do some work to help the community, but they might end up doing work where it makes a lot more sense to just like hire local people who are better at it and know more about it. So like there's a program called Engineers Without Borders in the United States. And they'll often send engineers throughout the world to do like infrastructure projects where they're like digging ditches. Do you think you have to ship like this guy halfway across the world to go dig a ditch? No, like that's ridiculous. And so I'm always thinking about what is my value added? Like why is it justifiable to ship me halfway across the world to work on a problem? I think it only is justifiable if I am bringing something to the problem, a capability of creating solutions that wouldn't be there otherwise. And so I'm always thinking about like, what is my value added that I'm bringing, and where could somebody else do a task where they would add more value than me? I shouldn't do that. I'm good at engineering and science and math. I'll do that stuff. Ditch digging probably doesn't make sense for us to do. So, building on this idea of value added, I think a big part is recognizing what knowledge do you have and where is your ignorance? And where can you gather more information to fill in around that ignorance? So in these pictures, the one on the left is showing one of my students who's holding the notebooks. And this guy worked on prosthetic knee design. He was a brilliant student, understood math and physics and biomechanics, really, really innovative engineer. But he has not lived a single day in his life with a prosthetic limb. And so the guy he's talking to, even if that guy has only 2 years of education, that guy knows a lot more about living with a prosthetic limb than my student ever will. And so it's important to understand like these other people who have sets of knowledge that you can leverage, and it's important to utilize that and interact with them as equals, as peers. Even if they don't have the academic pedigree as we do, they can still be really valuable. The picture on the right is showing some of the early work we did on drip irrigation with GIAN irrigation. And so a student is standing on the left with me, I'm wearing the baseball cap, and on the right, the guy in the striped shirt is the farmer who owns that field, and the guy next to him is one of the top engineers at GIAN Irrigation that designs drip irrigation systems. And so what I want you to think about is look at all the perspectives coming together in that picture. We're thinking about physics and engineering and innovation. The GIAN guy is thinking about production and the history of the products they make. The farmer's thinking about his needs. So think about bringing together all those perspectives and how if you can bring together this set of people, you can probably create something better than any one person could do alone. And I think in this slide, it's worthwhile to touch on a dynamic I've seen a number of times in India, actually, that I think is challenging for people at a university like IIT. You guys are all Indian, right? You grew up in this country. You may be totally socioeconomically different than a person in a village. And I've seen a number of times, I will work with people at high Indian institutions and they'll say, I'm Indian, I understand their needs, I understand what the village needs. And I'm like, no way. You're maybe just as separated as I am. We're at elite institutions. We may have had a privileged upbringing compared to these people. And so a big part of this, I think being a good designer is recognizing your own ignorance. Not just thinking like, I'm smart, I know everything, but saying, really reflecting on what do I know? What am I confident in my skills? And it may be around math and physics. And then what do I not know? And how can I go get that information? Right? So the objective of the next 2 days is that I want to give you a perspective, both from a technical standpoint and a socioeconomic standpoint, of factors that are relevant if you're going to design technologies for developing and emerging markets. And I think it's also valuable to recognize right now, I think if you're good at this, you have a great advantage over a person like me. I didn't grow up in this country. Right? I know you may have not have grown up in a poor village, but you still are from this country, right? So I think you have a tremendous advantage of like being here on the ground, designing for this context, as well as coming from a school like IIT Delhi, which is top in the world in engineering training. So let's start talking about what skills I think are needed if you're going to design for developing an emerging market. The first is it's so critical to define design requirements accurately. This is a classic folly of designers that I see all the time, where they have this great idea, they jump into a solution, but they didn't see the problem from the right perspective from the start. And so they work for years, create something new, they think it's great, but it fails in the real world because they didn't actually understand the context and the requirements they're trying to satisfy. So, for example, here's a product called the Life Straw. This was designed for communities that have to often drink from surface sources of water, like ponds or pools of water, and they would often be infected with a type of intestinal worms. And so they could drink water from the surface water through this thing, this Life Straw, which was a filter you could carry in your pocket. And so it gave you clean water anywhere you wanted to go. And so that's a really good idea. It was an effective water filter, it would get the worms out, worked really well. But when you look at this picture, how do you feel about it when I show you this picture next to it? Right? This person is bending down in the water, they're getting wet, they're putting their face right near the water, and they may be perceived like they're drinking the water just like an animal would. It may be demeaning. It may be disrespectful to them. And so I'm giving you this point because technically the Life Straw could be perfect, but socially, culturally, it could be terrible. And as engineers, we have to be very careful of this, right? I'm guilty of this too. I get excited about the technology. I like making things and designing things. But you can't be myopic about it. You have to think of the entire set of design requirements you're trying to satisfy, not just the technical requirements, right? The second thing is understanding consumer dynamics and unique dynamics in these markets. So what is this a picture of? Yeah, it's a slum, right? Maybe this is in Mumbai, or you see this commonly in the bigger cities in India. But what do you see on the top of all these houses? Satellite dishes, right? And so even though these people may be very poor, they may not be investing a lot of money into their house, they're still seeing a value in investment in television. And that is a powerful insight in that what do these people want to spend their money on? What do they value? What do they want? Not just what they need. A very common theme in like developing world technology is trying to make like a $300 house, right? Really low cost, nice house. You have to always ask yourself, who would pay for it and why would they pay for it? If everybody else in your community has a slum house, you don't even own the land, right? So you couldn't even necessarily hold on to it if you had a nice house. Why is there an incentive to put money into your house? Whereas if you compare that to television, right? If you have a boring life and you're just sitting around a lot of the time, TV is pretty entertaining, right? That's a good investment of money. So you have to think about people's wants as well as their needs. The next is realizing that there's a hierarchy of stakeholders behind a problem. User-centered design is very user-centered. We think about, like, let's say we're designing for a poor farmer, we need to think about those poor farmers' needs. But what you have to remember is that if you're going to create a solution, there's going to be a whole hierarchy of stakeholders, whole chain of stakeholders that are going to bring that solution to market. So you may have to think about production concerns. You may have to think about economic drivers of like a big company like Tata, and what do they want to get out of a solution? So you're not typically designing for a single stakeholder. You have to think of that chain of stakeholders whose needs have to get satisfied in order not to break the chain, so you can get an idea all the way out to market, to dissemination. And finally is this idea again of thinking about reverse innovation, thinking about can you leverage the same product platform with some modifications to make something that'll work in poorer contexts as well as in wealthier contexts. And so you'll hear a bit more later on about this product, the Leverage Freedom Chair, or some of the work I did on it here, which has the same DNA, but the one on the left is one that was made in India. The one on the right is now made in Taiwan and assembled in the US and sold in the US market. Same DNA, but tweaked a little bit between the two markets. Okay, So let's talk about some elements required for global engineering. I think when you are embarking on a new project, I think there's three core areas that are really, really important to reflect on to know that it's worthy to dive into that problem and you have some confidence that you could create a successful solution. So the first is identifying problems with merit. And what I mean by that is, are you solving a problem that deserves to be solved? I see a lot of projects in places like MIT where people will go to one village, make a single solution just for that one village that affects like 2 people. And it's like, if you're working in a country like India with over 1 billion people, is that actually making a big impact? Is that a compelling challenge? I'm not sure. So seeing like, evaluating, can you make impact? Who does it impact? How much? How big a population, et cetera? It's good to think about that. The second is, you may look at problems that are defined by or motivated by economics. Is there an untapped market? Is somebody positioned to make a lot of money by selling to a group of consumers that are not buying things yet? You know, and it's okay to be driven by economic opportunity, right? That's how companies work. And finally, I think it's so important when you're defining a problem to understand the metrics of performance that must be met for a viable solution. You know, if you're going to say, I'm going to make something cheaper, that's arbitrary. But if you can say, if I hit this price point, I'm confident people can afford it and it has enough value that they will buy it, that is much more specific. And you will be much more confident your solution is going to be viable. So it's so important that when you're defining design requirements, you know, talk about those metrics of performance that you want to hit and what would be viable, what would create a viable solution. The next in this Venn diagram that I think is important for folks like us who want to use technology to design in this space is, are you tackling a problem that has technical merit? And I think it's important to ask yourself, are you working on something that's actually a technology for development problem? Or is it a marketing for development problem? You know, if a marketing firm can just have TV ads and newspaper ads and be successful, done. It doesn't necessarily require engineering. So it's important to dig in and understand, does this problem need engineering to solve? The second is, can you leverage your technical insights for a solution? Does this actually require engineering and innovative thinking? Are you in a position to be a game changer in the problem? Or is it just something you can, you know, hand off to somebody else and it doesn't need rigorous engineering? And then for those of you who do research, I assume, are most of you grad students, by the way? Yeah. So for those of you doing research in this space, and for people like me, I always have to ask myself, is there knowledge to be created? I spend a lot of time with companies. I often have companies tell me, hey, I need to design this new thing. I see this market opportunity. We don't know how to design it. And I often have to say, you know what, I'm sorry, I cannot work on that because there's no research in it. It doesn't require the creation of new knowledge. You could solve this problem by just using existing engineering knowledge that you can look in books or that we've learned in classes and create this new gizmo, you know, this new device. But sometimes I find problems where nobody knows how to solve the problem. Like, you'll hear some examples in the next few days, but like, you know, in our drip irrigation work, we had to cut pumping power in half to lower the cost enough. There was no theory of how to do that. We had to invent the theory of how to do it to make the technology. That's the type of stuff that's motivating for me. And so I see, in contexts like ours, people who miss the mark because they're not seeing the overlap in these spaces. So for example, I see like developing world, emerging market classes in universities where maybe some students will watch some YouTube videos and they'll say, oh, I want to design for this slum in Nairobi and I have this perspective now, I'm going to go design it. You know, design this thing. And they have no problem merit. They haven't taken the time to understand the problem. Or I see people who like hack together a solution in an undergraduate class where they're not being rigorous about the engineering. They're just kind of, you know, sawing some wood and nailing it together, and they're making something crappy that nobody would want to buy. And so they're not putting enough technical merit into it. And actually, I see a lot of my colleagues at universities who have really powerful technical skills that could be relevant to problems, but they have no context of the market they may want to design for. Most of my colleagues are not going to go spend a month a year, in a place like India, like me and my group does, to really try to understand what are the requirements we're designing for. So be careful of whether or not you're missing the mark between these two. And then the final part of this Venn diagram is value merit. And so what I want you to think about when it comes to this is who's going to fund your work and what do they care about? I often care about science. I'm often funded by people who could care less about the science, but want the technology we're creating from the science. And so you have to tailor your work in your pitch, how you're explaining the motivation for your work, depending on who's going to fund it. If I'm appealing to a company, they want to make money. If I'm appealing to the National Science Foundation, they want science. If I'm appealing to our United States Agency for International Development, they want impact, right? So different stakeholders want different things. You have to think about what they want. You need to think about who's positioned to disseminate the work. Me as an academic at MIT, MIT doesn't make or ship any products. So I have to think about who would. How do I get them on board? How do I appeal to them? How will they disseminate our work? And finally, who's going to make money? I certainly bias towards solutions that could be disseminated through free market mechanisms because they're naturally incentivized to scale and be sustainable because you continue making money. So I try to think about, if I make something of commercial value, who's positioned to disseminate it, they make money, and then it reaches a large audience. And so finally, for you, I think it's important for you to reflect on what is your personal value proposition, right? Do you want to impact lives? Do you want to make money? Do you want to educate students, publish research? All of the above? And none of these are good or bad, but I think I see people oftentimes who are maybe just motivated by, they want to go change lives. They want to go save the world. But they're not thinking about who's going to make money to actually make that impact. So reflect on what are your motivations? What do you care about? What's driving you? So in all of this, when we come back to engineering, I think it's important to consider that we as engineers, the people at universities like this, in MIT, are really well positioned to create what I call the technological keystone. And what I mean by that is that oftentimes, let's say, for example, we're working with a company. The company knows how to make products. The company knows how to ship products. The company knows how to market products. But what they don't know how to do is make this technological advancement that would enable them to make a whole new line of products to reach new users. That is the little technological keystone that I'll take on, right? That's leveraging science and innovation, the things we're good at MIT. I'll do that, but I try to build around it the resources from other partners to take it to market, right? So think about what is that value added? What is that keystone of the problem that you can add to create a solution? Okay, so now it's time to design. So we'll keep going. We started about 15 minutes late, so I'm going to go probably closer to quarter of. All right, so let's talk about design process. Who's taken a design class? Has anybody here taken a design class, where you learn design process? Oh, this is great. It's no problem that you have? Okay, good. Also great. No problem. So let's start by talking about why is it valuable to use a design process. Let's take, for example, let's imagine you have this great idea of a spaceship that can put a man on a moon. And let's try to imagine what it would take, all the engineering it would take to make that rocket. It's impossible to hold that in a single person's head, right? No one person has all the tolerances of every part of that Saturn V rocket in their mind. Design does not work like this, right? Design enables you to take big, otherwise intractable problems and break them up into small parts so they're manageable, and you can generate multiple ideas, pick the best ones, put those ideas together, and make a viable solution, right? So it enables you to break down hard problems to make something awesome that you couldn't just keep in your own mind, right? It's actually a dedicated process that you follow. So let's talk about using a design process and important points about this. The first is it enables you to break a very big, difficult problem into smaller, more manageable chunks. My heroes in engineering and design are these guys. Do you know who they are? Yeah? Who? No, not Tesla. They're two brothers. The Wright brothers. Yeah, the inventors of the airplane. And I think what they achieved in human history in regards to technology is unparalleled because of how they broke a crazy intractable problem into chunks. So let me give you a little background on that. In the late 1800s, around 1899, Wilbur, which is the guy on the left, started getting interested in flight. And they started studying up on flight and studying wing shapes that would give a certain lift to drag ratio. They started making gliders and experimenting with flight. And the leader of the day in flight was this guy named Otto Lilienthal, who made these gliders. They were like bat wing type gliders. And he would jump off cliffs and glide, and he eventually killed himself crashing these gliders. But anyway, he was the leader of the science of flight. And so the Wright brothers, being good academics, they read about the background of the work, and they said, all right, we want to make a glider based on his lift to drag tables of wing shapes, right? So for a given wing shape, you could know as it's moving through the air, given the velocity, how much lift it'll make and how much drag it'll experience, right? So they made a glider, and they realized it didn't work anywhere close to what was predicted by Lilienthal's tables. And so the first part of this story, what's amazing about these two guys, is they were the inventors of the aircraft, but the starting point of information that they had was wrong, right? So to put this in context, if you went into your backyard and made a space shuttle tomorrow, that would not be, launched to the moon or launched into space, circled the globe, came back, that would not be, I think, as great a technological achievement as what these guys did, because you can go to the library and read how to design a space shuttle. Like if you read long enough, that information's out there, it all exists. But these guys had nothing. And worse than nothing, they had wrong information. So instead of making gliders that crash and killing themselves, they took a step back and said, let's think about how to break this problem into chunks. So the first thing they did was think about how to make a wing perform as they desired. And instead of making big wings in gliders and jumping off a cliff, they made little wings out of sheet metal and put them on this balance. This is a balance that they put in a wind tunnel that they made. They made only the second wind tunnel in the United States at that time. And they made the engine that powered the wind tunnel. Like these guys were unbelievable in what they made. But they made this really simple experimental device where they could make, this is the wing right there. So they could put this in a flow of air and measure how much lift the wing makes and how much drag it makes. And they tested hundreds and hundreds of wing shapes, and they could do it cheaply, safely, efficiently. So they found a wing that gave them the performance they wanted, and they also characterized the wing so they could predict, given a certain wind speed, how much lift would they get for a whole airplane and how much drag they would experience. Then they took that wing shape and made gliders. So they first had gliders where they ensured their wings worked, and then they incorporated control into their gliders. That was the second part of an airplane that they had to master. And their big insight in airplanes was realizing that in a turn, you had to lean, right? Just like on a bicycle. And people think that maybe it's because they were bicycle makers, they realized this. But their contemporaries, their competitors at the day, thought you would fly a plane like a ship. It would just fly in a single plane of the air, and it would just turn just like a boat would on the surface of the water. The problem is, as you make a turn, your outside wing gains airspeed and lift, your inside wing loses it, and you can crash. That's why you have to do a bank turn. And so they developed a wing warping system, which was a kind of rudimentary means of ailerons to tilt the plane, as well as rudders, as well as elevators, and they mastered control, right? That plane had 3 degrees of freedom of control. Then, what they realized is they could characterize lift to drag, they could control the plane, and because they knew lift to drag, they could calculate how much thrust power they would need to move through the air to get enough lift, right? Thrust force times the velocity is thrust power. And so when they were designing the first flyer, they realized they needed 8 thrust horsepower. That's the drag force multiplied by the velocity. And they figured they could get a 66% efficient propeller, and so they needed 12 mechanical horsepower coming out of an engine. So they needed a high power to weight ratio engine, and they talked to a bunch of engine manufacturers, and nobody would make them an engine that was low enough weight and high enough power, so they made their own. In their shed, they had a little shop. They cast their own block, they made their own 4-cylinder engine that was 12 horsepower. Then, when it came to the propeller, the leading theory of the day was that airplane propellers would work just like ship propellers. So the Wright brothers, being good, diligent engineers, read all about ship propellers. And it turned out that there was really no theory behind how ship propellers were designed. People would just kind of design them by eye. And so the Wrights figured out that a propeller is just a wing with a changing angle of attack as you go from the root of the propeller out to the tip that's moving through the air in a helical pattern. And so they ended up designing the most efficient propeller ever made for the Flyer that hit their efficiency mark, 66% efficient. So because they broke this crazy hard problem down into small chunks and solved it one piece at a time, lift, control, power, they put it all together, they predicted that an airplane could fly, and it worked. And it basically worked on the first try. They had a little bit of issue in the propeller shafts. They were weak and they'd vibrate and they broke, so they fixed those. But once they fixed those, their first plane flew. And they knew it would fly because they solved each of those problems one at a time. Now, in contrast, oh, by the way, I should add, neither of these guys had a college education, and they did this as a hobby. They were bicycle mechanics. They did it on their own time, in their own money, and they made the first successful airplane. That's why these guys are the kings of experimental science. But anyway, to put that in contrast, one of their big competitors of the day was this guy named Langley. And if you're familiar with the Washington, D.C. area of the United States, there's a place in Virginia, the state of Virginia, called Langley that's named after this guy, and it's where the Central Intelligence Agency, or CIA, is located. This is a big guy in U.S. government history. At the time, he was the head of the Smithsonian in the early 1900s, which was the nation's main scientific research organization. He had limitless resources, and he was making experimental aircraft. And the aircraft he would make were biplanes. So this is a biplane where it has two longitudinal sets of wings. And he built this barge, which had a catapult on it, and he would catapult the planes into the air, and they'd crash into the Potomac, into the river. This is on the Potomac River. And so he'd make a plane, crash, make a plane, crash. And so the Wrights beat him. They made the first plane. But a number of years after the Wrights first flew their plane, the Smithsonian contracted their big competitor, a guy named Glenn Curtiss, to retrofit Langley's aircraft to put a more powerful engine on, tweak the wings, and they were able to get the plane to fly really low in ground effect. But it did get off the ground. And so the Smithsonian, because they wanted to give their own guy credit, said, we are going to jointly credit the Wrights and Langley as the inventors of the first heavier-than-air aircraft. And the Wrights said, no way. We are not taking that. We're not accepting that. And at that time, the Smithsonian wanted to display the Wrights Flyer, the aircraft. And they said, no, we are not letting you display it until you give us sole credit as inventors of the first powered aircraft. So they bickered back and forth for a long time. But finally, I think around the 1920s or 30s, they finally acquiesced and said, okay, we will give you sole inventors of the first powered aircraft. And it was only after World War II that the Smithsonian was able to get the Wright Flyer, bring it to Washington, D.C., and display it. Because during World War II, it was actually in England in display in their Smithsonian equivalent. And during the war, it was too dangerous to bring across the ocean because the Germans could sink ships. So they had to wait after World War II, display it. And now, if you go to Washington, D.C., you can go see this in person. And what's amazing, too, is the Flyer is just like a bench-level prototype. It's kind of crappy. It's like wood and bicycle parts, and it's all handmade. But the Wrights kept it. It actually was almost destroyed in a flood, but it still exists. And I think the Flyer is the most holy relic of an engineer, for an engineer. And so actually, whenever, I'll talk about that in a second, but whenever I go to Washington, I actually go visit the Flyer. So here's me in front of the Flyer earlier last year. And it's just, I love being in its presence. It's like the most beautiful prototype ever made. So, some important points here to learn from the Wrights is not only break big problems into chunks, but also think about how can you fail early and often and not catastrophically. The Wrights did not want to die making an airplane. They really tried to mitigate risk by doing bench-level tests. smaller, in the lab tests, so they didn't have to put themselves in the air and potentially die. And I think that's important for us engineers. And you also want to fail as quickly as possible. Another folly I see all the time of designers who design for poor countries is they maybe work for 5 years in the lab, and then only realize after that what they created is too expensive, or people don't like it because of how it looks or something. My group is in the field every 6 months testing prototypes. Like here in India, I've got most of my lab group is around the country right now, testing different things. And we're trying to figure out, what do we not know? How can we fail as quickly as possible? Because then we take those failures, iterate, and make it better. And just, if you like that story I just told you, you can read this book, Wilbur and Orville by Fred Howard. It's a great book that tells the story of what these guys did. So the next point is more ideas tends to lead to better ideas. A classic mistake a designer makes, particularly students, is they come up with a legitimately great, brilliant idea, and they say, okay, I'm going to go design it. And they don't take the time to step back and say, could I make it better? Could I iterate on it? Could I come up with different variants? Maybe there's better ideas. Or maybe they're working in a team and they say, oh, I want my idea to be made by the team, so I'm going to push my own idea. And that's silly. Strive for the best idea, even if you didn't come up with it. So as an exercise, I want you to design a solution for cleaning up dog poop that doesn't, from your lawn, that doesn't require picking up with your hand. If you go to the US, particularly in cities, you see people with dogs all the time with these silly gloves on, picking up their dog crap off the ground, right? And they have to pick it up with their hand and throw it away, and it's kind of gross. So what are some ideas of how could you do this without touching the dog crap? How could you do it? Think of a way. Can you think of a machine to do it? Like a vacuum cleaner, yeah. You could vacuum the lawn and it would suck up all the dog crap. What else? Flexible gripper, yeah, that's a good idea. Yeah, so you see people pick up trash that way, right? To grab the thing, yeah. What do you think? What are some other ideas? About just like a shovel, right? A scooper, right? And you scoop it off the ground. So these are, you're touching on real products. Here's the vacuum cleaner. Here's the scooper. Here's a bag that scoops in a little different motion. There's kind of a rake system. Here's a gripper system. These are all great. But this was a bit of a trick, because I said design a solution for cleaning up dog poop from your lawn that doesn't require touching it with your hand. And why that was a trick is I led you to thinking about devices, but a solution doesn't have to be a device. You could think about, what about attaching something to your dog, right? It walks around and craps into a bag. Or what if you train your dog to go to the bathroom in a certain bin? Or what if you train your dog to only go to the bathroom in the woods outside your lawn? What if you buy a cat? Cats don't make dog poop. Cats make cat poop. So a cat cannot poop dog poop on a lawn, right? It's physically impossible. No, I'm serious. So the trick I'm playing is I defined the problem in a way to lead you to thinking about devices. But it's important, as you're generating many ideas, to expand your scope of how you think about it, right? I said, all we want to do is prevent dog poop, or prevent you from having to pick up dog poop from the lawn. Another idea, what if you have a house without a lawn, right? There's no lawn at this house. So even if there's dog poop on the ground, it's not on the lawn, right? So I'm looking at the problem from different angles, and these are all viable solutions that meet that core requirement. So that's the last point here, is that it's so important to define design requirements independent of the physical solutions, the physical devices you might make. So an example of this that I like a lot is the Gates Foundation's program called Reinvent the Toilet. Now I'm saying that noun, that device, a toilet. But what is their core requirement in their program? If you read at the bottom, reinventing the toilet can save millions of lives and help end poverty. What is their goal in this program? What is the requirement they're trying to meet here? What do you think? Why do they want better toilets? To save lives by hygiene. Yeah, preventing people from ingesting waste, right, and getting sick. Okay. So if you call this program and you focus on reinventing the toilet, that's just as arbitrary as maybe calling it reinvent the sewer, right? You could reinvent the sewer and prevent people from getting sick. You could reinvent the people, right? Reinvent the colon, reinvent their digestive tract. So it they don't produce pathogens. Right? Why not think of that idea? So they artificially are constraining their solution space with this title to only thinking about toilet design, right? And I think that's a problem. I think a lot of the devices they've made are around toilets, but and to be fair, they've also thought about like whole systems. They're not just designing toilets. But I think for a designer, when you read that, it artificially constrains you to thinking about toilets only. And it's important for us as designers to back up and think about what are the core requirements we're trying to meet, and could we think about totally orthogonal directions like reinvent the colon, Okay, so here's a famous picture of what a design process looks like. And it starts really messy. You're doing research, you're getting your requirements, you're generating a lot of ideas, and then you start applying analysis, testing, refinement, and you refine down that noise until you make a concept prototype and do some testing, and you get more and more clarity, and you end up finally with a refined single design. So when you think about a design process kind of roughly, it looks like this. Now more formally, this is kind of the canonical work on design process by folks called Paul and Beitz. They were, I think in the 70s, they were Germans that really kind of formalized this process. But it's a similar process. We're designing this product that looks kind of like a duck's head. There's a duck bill and there's the head. And so this process works by first planning and defining your design requirements, and then generating many, many ideas, your concept development, and then refining those down, doing system level design, detailed design, testing, refinement, and then finally producing a product. And in each stage here, you want to go through a number of sub-stages where you want to understand customer needs, your specifications, generate multiple concepts, figure out how to select the best one, et cetera, et cetera. And all these arrows are also pointing back because it's important to be iterative. You want to be stepping back and saying, did I do the did I make the right decision the step before? And does it make sense, the progression I'm going in, the path I'm going in? Now, to give you an example of this, let's look at what if you wanted to design eco-friendly supercar, right? And this happened. This happened with a number of companies a few years ago. Porsche, Ferrari, McLaren all did this. And so Porsche, they ended up with the 918 Spider, but let's imagine we're Porsche, and we want to do an electric supercar, an eco-friendly supercar. At the strategy level, we can start thinking about what are different ways to potentially reduce the use of fossil fuels in a car through different strategies. So you could do some energetic calculations around diesel electric, gasoline mechanical, gasoline pneumatic, reducing the vehicle's weight. And notice when I say all those words, you don't see a picture of a car there. What's important about the strategy level of design is you want to try to keep yourself as agnostic as possible, not locked into a physical conceptualization of your solution. And we're going to do some more examples of this later, but like thinking about, from a strategic standpoint, how can I make the right decision of what strategy direction to go in? And actually, all of these ideas have been pursued by different companies at this point. But Porsche ended up choosing gasoline electric. So then they had to create a concept. And the concept of that drivetrain was a V8 motor with an electric motor assist. And so they conceptualized this, and then they could break it up into smaller parts, just like the Wright brothers. So it's hard, none of us can conceive all the parts in that entire vehicle. So they broke it up into different modules, and here's a picture actually of that car's drivetrain modules. So in the front wheel drive, you have an electric motor that drives the two front wheels. Then you have a gas engine, an IC engine, a battery pack, and another electric motor. So it's got electric motors on both the front and rear wheels. And then you refine that down into like a most critical module design, let's say the battery pack. And then you can go into the part design. So here's all the part designs of, this is actually the battery pack of the 918 Spyder. So in this design process, we're taking a big problem, breaking it down into small chunks, small little parts, and then we'll build back up the solution to the final embodiment. And so that's kind of the bottom-up approach. You break it into little small parts, and then you build it up from that bottom into the full solution. Now, to contrast that, I think it's also important to think about a user-centered perspective. And when you're thinking about the user of a vehicle like this, you need to like ask people what they think, you need to observe what people are doing, you need to experience it, and we're going to talk more about this ethnographic type research a little later on. So when Porsche started designing this, these two pictures are renderings. This is not a real vehicle. These are artistic drawings. And so they could show these to people and see like, how do people experience this? How do they feel about this, right? Before they went and made the prototypes. These are actual physical prototypes. So this would be kind of what I would call a top-down design process, where you're thinking about the entire finished product, how it's going to interact with the user, right? And think of its whole conceptualization. So they could get feedback from consumers, feedback from test drivers with this kind of like top-down, fully integrated solution approach. So as a designer, I think it's important for us to balance both these technical and user-centered factors, but also balance this top-down and bottom-up approach. Like certainly, if we're designing like a big complicated system like a car, we have to break it down into small parts. But you have to still remember, it's a car. It's a fully integrated product that's going to interact with people. And so Porsche was able to do that with the engineering and the rendering work. I just have a few more slides to finish up here, and then we can take a break. But some additional points to consider is think about who lead users are. And these are people who are very attuned to the behavior of a product that could give you really valuable feedback. So does anybody know who this is? It's Jeremy Clarkson. He's a British car reviewer. You know the show Top Gear? You've probably seen the magazine here, Top Gear. Yeah, he was really popular with Top Gear, but he's known for being very critical of cars. And so companies will give him cars to test because they know he will give them critical feedback. He won't lavish them with praise. He'll just say, no, this car is crap, and here's why. Now, when we were doing the wheelchair design, we had to think about this too. Right, here's a guy who's like really jacked. He would ride a wheelchair off-road. He was in Tanzania. He'd ride his wheelchair like 2 kilometers a day, a regular push-rim propelled wheelchair. So we gave him one of ours and had him test it, and he gave tremendous feedback because he knows how to ride a wheelchair off-road. Right, he is a lead user. He's one of these people that knows the product and its weaknesses and its merits more intimately than just a normal user. Also think about latent needs. So a latent need is a need that a user may not be able to express explicitly, but is still really important to a design. So do you know who this guy is? This is Henry Ford, who started Ford Motor Company. And he has a classic quote that if I asked people what they wanted, they would have said faster horses. Right? So at the beginning of the 20th century, before cars were popular, people still wanted to get from one point to another faster. Their frame of reference was horses, right? So they would say, oh, if I could have a faster horse, that would be valuable to me. Now, the latent need that they're saying is, I want to get from point A to point B faster. It's not that they literally want a faster horse necessarily. So Ford thought about, how do we make cars that can provide that function? Who would you say is one of the leaders of reading latent needs in our generation? Who is so good at designing products that people really want even before they know they want them? Tesla, so yeah, Elon Musk I would say, but also Apple, yeah, Steve Jobs. Yeah, he was really good. The iPhone, the iPad. Like if you had described an iPad to me before I saw one, I'd been like, what? That doesn't sound useful. And then they sell millions of them, right? Another important point is like be very careful not to impose false constraints on your design. And so a lot of those that I see when you're when designing for developing or emerging markets is things like, oh, it has to be low cost. It has to be made from locally available materials. It has to be given away for free. It has to be of substandard quality of what like you and I would buy. All of that's bogus, right? It all depends on the conditions of the market and the actual design requirements you're trying to satisfy. So don't tie yourself into those. And as a counterexample of that, this is a variant of a Ferrari, the 458 China edition. This was designed specifically for the Chinese market. Right? Ferrari didn't impose any of these false constraints. They did some things to make it particularly appealing to the Chinese market. You can see like the dragon on the hood and stuff. But yeah, they didn't compromise that because they recognize there is a market for Ferraris that want a high quality product. So to juxtapose design constraints, think about design freedoms. These are aspects of the market you may be designing in that you can really leverage to your advantage. You can utilize to help you. And so things that you might find in a developing and emerging market is, or in any market, is thinking about like, what are humans really good at and what are they bad at? So humans are really good at dexterity and perception. If I want to identify like one color object on this big table, I can do it relatively quickly. I can locate it with my fingers. I can pick it up and put it somewhere else. People are not good at like high power or high force activities, like lugging dirt around in a wheelbarrow or something. So think about what you can leverage and what may be limitations. Things like subsidies. Subsidies change in every country. For agriculture in this country, you have really powerful subsidies, way more so than we even have in the US. Think about the entire economic pyramid, not just poorest of the poor, but what does the whole ecosystem look like? Are there specific parts and materials that are easily available in this country, but maybe not somewhere else? Are there different environments? So for example, doing solar powered systems in India, easier than in Boston. You have a lot more power available by the sun. So I think maybe, why don't we stop right now and take a break, and I'll pick up the presentation after the break. So I think this is a good stopping point. But do you have any questions before we take a break? You guys are quiet. I'm going to want you to.
No questions.
You're going to speak more. There's more interaction coming up. Yes?
So, I'll give you an example of Apple trying to develop products with the latent needs thing. But isn't it possible that we are being forced to use something that we don't actually want to? Means something, suppose an iPad. So there might be a requirement that we never needed an iPad, right? But just because it's there, we are using it. We were happy not to be using it. So this can also happen.
I think, well, you're bringing up a good point about, I think, being cognizant of forcing people to use things, but I wouldn't say you're forced to use an iPad. You have, as a consumer, you have the decision of whether or not you want to buy it. But I think in regards to some medical devices, I've run into this with wheelchairs, where people are sometimes forced to use a poor quality wheelchair because that's all they can get. Like that's all they can get for free from a hospital. So as consumers, they have no way to provide feedback and provide pressure to create a better product. You can provide pressure on Apple to create better products by not buying them. Apple is so wealthy because they have made good products that people want. So I think that's different than being forced. I wouldn't use necessarily the word forced.
Not exactly forced means it's some, there can suppose if Ferrari.
Yeah.
So a person, society would not necessarily need a Ferrari.
Yeah.
So if a designer want to create an impact, he won't try to improve on Ferrari or try to, maybe if I feel that iPad is not required, then means that can be a different viewpoint, but it's not necessary that something such as an iPad would be required in the society, even latently. It's different from a vehicle because I wanted to move from point A to point B, but not similarly to for an iPad.
So this is a very important point. Don't confuse people's wants from needs. They're two different things. And a big mistake designers make, particularly when designing for poor markets, is they only design for people's needs. People don't always do what they need. You know, we wouldn't have diabetes, we wouldn't have drunk driving if people only did what they needed. They do what they want. They eat too many sweets. They drink too much alcohol, right? They buy televisions instead of improving their house or water quality. You know, so a Ferrari designer is appealing to people's needs. Yes, a Ferrari serves the same purpose as a Tata Nano from getting to point A to point B, but it looks awesome. It's fun to drive. It sounds amazing. You know, that's why they sell Ferraris. So as a designer, you need to be cognizant of that. If you design only for people's needs, or particularly your perceived needs, you very well may miss the mark and get it wrong. Because your needs may be different than the consumer's needs. But that's a good point. Thanks for bringing that up. Yeah?
So, while you were explaining about the Wright brothers' design for the plane, you told us first about it. They worked on the lift problem, then control problem. But in sometimes like during design, like when they were solving about control problem, they might have realized that it is not possible from the lift problem perspective.
Mm-hmm.
Like all the things can't be done parallelly in this case. So won't be here the recursive loop will be fixed in the recursive loop, that if we try to solve this problem, then we are fixed in this in the same problem, like in the bottom up approach. So isn't the top top to bottom?
I think that's a good point. I think you can't be myopic about some modules of a design. You have to think about their integration with the rest of the other modules and with the market. And I think, you know, where that comes in is how you define your design requirements. You know, if you, let's say you're designing a battery system for a hybrid car, you can't just think of energy and power. You need to think about cost and weight. You know, the battery's core function for providing power and energy is like that's one function in regards to the overall car, but you also have to think about vehicle dynamics, right? Of like, where's the center of gravity of that battery? How much does it weigh? And so when they're and I think this comes back to the top-down versus bottom-up approach. Like if you're laying out a car architecture, you're going to do some initial calculations, modeling where the center of gravity could be, how much the car weighs, the suspension stiffness, all on a pretty like high-level conceptual level. And then you're going to say, all right, the requirements for the battery pack are this weight, this size, and it has to include so much energy and power. And so by doing that, you are capturing some of the additional design requirements beyond the core function of the battery, but are going to be important to incorporate it into the full vehicle. So yeah, you can never, this is what's, I'm glad you brought this up, because I think students struggle with this sometimes because they want to follow a design process and they do step A, step B, step C, but it's not as regimented as that. You can't just look at each problem like this. You have to think about what are the down the road effects. And part of the way to address that is build in some iteration too. You know, when you come up with a concept of like this battery pack, then ask yourself again, is it light enough? Is it small enough? And you may have to redesign it a little bit. Yeah.
I think the problems are because background controls. So what the Wright brothers did is they did not control, so he mentioned the ship, right? You control the direction of a ship by using its rudder, right? So it's a completely different force mechanism from what the propulsion mechanism is, right? And because you did not want to go very fast, and also the keel mechanism generates for small deviation very large forces, it worked. Wright brothers were the first to realize that they need to change the aerofoil shape to generate differential lift.
Well, yeah, but that was for stability in a turn.
Yes.
Yeah, it wasn't for turning torque.
Yes. You cannot achieve stability without changing aerofoil shape. They were the first people to realize, and that is the fundamental thing about control, is that you ask what mathematical structure gives me a control which is stable. So they are not really worried about the parameters themselves. So it's actually a top level design which they changed around. So unless you have the right top level structures in place, you cannot do the refinement, you cannot do optimization unless you have the right. Once you have the right structures, then you want to run a very large program to optimize across the whole system. That's what you can do now. But there's no point doing finite element unless you have your degrees of freedom right.
I want to make a point too that to get those degrees of freedom right, there's multiple ways to do it. There's mapping out the whole mathematical construct, and I think we learn about that. And, I do this too. But there's also ways to do it empirically, which is what the Wrights did. They made test devices, right? They made gliders. They made small models. The Wrights were not writing out the mathematical equations and calculating the exact aileron area and stuff and momentum change of the flow, but sometimes you'll work on designs where there's so many variables, you just need to test it. You need to make a prototype and test it. Where I see that a lot is when people interact with it. Like if I need to measure a person's response to a product, I can't mathematically derive that oftentimes. I need to go test it. We'll make a prototype and go test it. Sometimes we'll make a model that looks like a real product but doesn't work like one. And they'll say, oh, this is how I think it looks and feels. Sometimes we'll make prototypes that work like the real product but look like a prototype. So they can feel like, how stiff is it? How does it feel to maneuver? So think about that, there's an empirical way to test, to analyze things, and there's an analytical way too. Both are tools that you have at your disposal. Good points. This side of the room, any questions?
One question, that in your freedom share,
Yeah.
you have done bench presses
Yeah.
for the mechanism, but in India we have a bipedal mechanism.
Yeah.
There too. That is a very effective or easy.
It is. It's a very good mechanism. And it is used successfully on hand-powered tricycles that you see throughout India. There's some where the pedal's in front, there's others with a pedal on each side. We did not use that drivetrain for a few reasons. One, it doesn't necessarily enable you to go backwards when you're like indoors. So with our lever system, you can take the levers off and just use it like a normal wheelchair. The other is that you have a single gear ratio with those pedal systems. And we wanted to make a product that could go fast on flat ground, but also climb up hills and go through mud and sand. And we achieved that by moving our hand position up and down the levers. And so we get I'll show you this more tomorrow, but you get a range of mechanical advantage by doing that where you could not with a crank drive. There has been other wheelchairs with crank drives, but the lever drive we did enables a higher level of flexibility in operation, and that's why we chose it. So should we take a break? Tea break? Yeah, 30 minutes late. We're getting off to a good start. 30 minutes late. Okay, stop recording. Good.